quick review of strong acids and strong bases and important players in pH acid-base theory. There's your strong acids, strong bases. As you can see, they're all protic. Sulfuric acid is what we call diprotic because there's two hydrogens, doesn't make it a stronger acid. And likewise on your bases, most of them are monobasic. A few of them are what we call dibasic. Important players in pH theory would of course be water, which is neutral. And we can think of water as HOH or proton and hydroxide. And proton, hydroxide, and hydronium. And the key equation that explains pH is, again, little p stands for minus log and H stands for hydrogen ion concentration, which nowadays is more appropriately called hydronium ion concentration. And lastly, quick review would be the pH scale runs from 0 to 14, with 0 being the most acidic, 14 most basic, and 7 basically neutral. And that's a reflection of the amount of hydronium. And we use this pH scale because it's a nice number system. As we'll see, the hydronium numbers are as human friendly. But as the hydronium molarity, which is indicated by those brackets, goes up, the pH falls, and we again say it's more acidic. Continuing on with Arrhenius, as a quick review, we talked about HCl making hydronium, and of course in order to do that it would need water. And then logistically we have to include the chloride ion. And even though it's technically reversible, we like to say that it's largely shifted to the right, or it favors the formation of products. Another way to describe it mathematically is what's called the K value. And the K value stands for equilibrium. And the K, the equilibrium expression, is always the product's concentration divided by the reactant's concentration. And the brackets indicate molarity, or moles per liter. And a lot of times we like to make new Ks to make our lives easier. And in this case, the new K we call Ka for acid. And we shove the molarity of water into it, and thus Ka expression you'll commonly see like that. So again, another way to say that HCl is a strong acid is it has a large Ka value, often quoted as 1 times 10 to the minus 7th. That just is a 10 million, big number. It just means there's a lot more of those, the products, than the reactants. So essentially it's fully converted over to hydronium and chloride, and that's why we can say that HCl has a low pH. So for example, if we talk about 1 molar HCl, and we put this into practice and we can ignore the reverse arrow, we would say the amount of molarity of hydronium is 1 molar, and there's really no HCl left. So a bottle of hydrochloric acid is really a bottle of hydronium and chloride. And we again ignore the water for this. Where I'm going with this is if we know the amount of hydronium, as in its molarity, we can then calculate the pH through that equation. So, giving you 5 seconds, plug in 1 for the molarity, and you should come up with a pH of 0. So a pretty concentrated 1 molar solution of a strong acid should have a pH close to 0. Now what's going to happen if we take something like acetic acid, which is not a strong acid? And again, you're going to know that because you're going to memorize your strong acids. And if it's an acid because it has an H, but it's not one of those acids, then it's not a strong acid and it therefore must be a weak acid. According to Arrhenius, any acid with water is going to formulate hydronium and what's called the conjugate base, which is what forms when the acid gives up its proton. So the conjugate base of that equation would be acetate ion. Long as we're on conjugates, we would call hydronium the conjugate acid of water. Conjugate acid would be whatever forms when something acts as a base. Similarly, we can set up an equilibrium expression either with K or Ka for acetic acid. The important difference between acetic acid, a weak acid, and hydrochloric acid is the K value for acetic acid is 1.8 times 10 to the minus fifth. And as you can see, it's a much smaller number. So now we really have far more reactants than products once our system gets to equilibrium. And again, for completeness, the equilibrium expression would look like that. Where this represents the original acetic acid concentration, that's going to represent the molarity of hydronium formed, and that's going to represent the molarity of acetate formed. And if we don't add anything else other than pure acetic acid to water, these two must be equal, and then you can do a whole bunch of mathematics and get a quadratic and solve for hydronium. We're not going to be responsible for the quadratic approach, but if we can solve for the hydronium, then the important thing is once we know hydronium, we can convert to pH. To give you a feel for that, if I use the same molarity acetic acid, 1 molar, we get, after the mathematics, which would look like 1.8 times 10 to the minus fifth, and we'll make that x and that x because those have to be equal, and then the concentration of acetic acid is 1, and then we would do some math and we would have x comes out to about 0.0041 or 2. And that would again represent the molarity of both the acetate and the hydronium. And for this, we're really interested in the molarity of the hydronium because that'll allow us to get to pH. So the pH here is going to be the negative log of hydronium, which in this case is 0.0041. And given you 5 seconds, if you plug that in correctly, you should get to a pH of about 2.39. Thus, we can see that the equal molarities of a strong acid and a weak acid do not give us equal pHs. So even though it's the same amount of acid, they're not the same pH. So pH does not measure the amount of acid, it measures what we call the acidity. And you might say, well, not a big difference between 0 and 2, but alas, it is a big difference because again, the pH is a logarithmic scale, so each change in 1 unit of pH represents a 10-fold change in hydronium, which is really what we're talking about with acidity. So if we roughly say this is 2 orders of magnitude lower than this, we would say this is 100 times more acidic than that. So one jump in pH unit represents 10-fold change in acidity. Erasing the board. Next up would be comparison of or examples of some weak bases. Magnesium hydroxide, even though it's a hydroxide, is a weak base largely because it's not very soluble in water. So even though what does dissolve will dissociate into free hydroxide, and you get 2 hydroxides for each magnesium hydroxide. And again, water is your solvent, and that both dissolves and dissociates ionic compounds. So again, magnesium hydroxide, not a strong base because it doesn't have a high solubility, but it does dissolve a little bit and give us some hydroxide, and thus it is a base but not a strong base. And then there's other bases. A classic example would be ammonia. So if you're told ammonia is a base and you're shown water, then you should automatically know again, ammonia is not one of your strong bases. So if you're told it's a base, then it must be a weak base. And according to Arrhenius, any base with water is going to formulate hydroxide. And if you look at that, you should be able to pick up on the hydroxide comes from the water as the water loses one of its H's as a proton again. So then logistically we can say the proton went from water over to the ammonia, so the ammonia must have become ammonium. So that's how ammonia and water react to make ammonium and hydroxide. And again, notice water here is taking part in the reaction. Water here is just a solvent. So a lot of your bases are hydroxides, but not all of them. The important thing about bases is they make hydroxide. This, as said, is a weak base. So in 5 seconds, what can you say about the K value, which in this case we're going to call KB? The KB can't be very large. We can't ignore the reverse arrow, so therefore the KB must be very small. I don't have the number in the top of my head, but this equilibrium is largely shifted. So a bottle of ammonia is really not much hydroxide. There is some, but it's more ammonia and water. And that's commonly used as a cleaner. You might know of it as Windex. To complete this, if this is a base, the conjugate acid would be ammonium. And in this case, since the ammonia is a base, it's calling out water to act as an acid, and thus the hydroxide would be the conjugate base. And another key equation we're now going to get into is derived when we look at the reaction of water with water. May seem redundant, but it's very instructive. in the sense that if you treat one water as the acid and one water as the base, the proton is going to move from acid to base, and we're going to form hydronium and hydroxide again. And in this case, if the hydronium and hydroxide only come from two waters, in other words, nothing else is added, then the equilibrium expression looks like that. And we would have two waters on the bottom. And again, we take the molarity of water and we shove it into the new constant, and we call the new constant Kw, and that's equal to 1 times 10 to the minus 14th, and it also is always equal to the hydronium concentration times the hydroxide concentration. So Kw, and this is a need to know, its value is 1 times 10 to the minus 14th, and that's at 25 degrees Celsius. It does change if the temperature changes, but for our purposes we're going to assume it's a constant, and we're always going to be working at 25 degrees Celsius. So with those two equations and the pH equation, now we're going to be able to relate hydronium and hydroxide to the pH and to each other. The simplest way I'd like to start would be if hydronium and hydroxide are equal to each other and they're unknown, we can call them both X. And if we always know that Kw equals those two multiplied together, and we know Kw is 1 times 10 to the minus 14th, we can say 1 times 10 to the minus 14th is equal to x squared. And I got x squared by just making hydronium x and making hydroxide x. And again, those two are only going to be equal to each other in special circumstances. And this circumstance would be if we had